Okay, I'd like to get started again. And I want to continue talking a little bit about how one, either from the bottom up or the top down, one makes composites of nano ingredients into, say, micron size systems. Okay, and the example I got here is a technique using electrospray assembled nanoparticles. So in this particular case, I had this work was done by Mike Zachariah. He basically had a solvent, and in the solvent, he mixed nitrocellulose and nanoparticles. He put them through an electrospray system, and as they went through the electrospray system, it created very, very small droplets. Basically, the solvent would vaporize, and what was left in the particle then was the nanoparticles of aluminum and the nitrocellulose. Okay, and he then controlled basically the size by capturing them before they got too large. And so what you're seeing here is basically that sort of idea of being sprayed, capturing them, and he ends up then with a gelled microparticle. And some examples of the combination are the particles shown here with nanoaluminum, nitrocellulose. He's made nanoaluminum, ammonia perchlorate, nanoaluminum, RDX type particles. So they're composite particles. And the idea again then is if I got this interstitial material, in this particular case nitrocellulose, say, at what temperature does the nitrocellulose come apart and gasify? And so he's actually seen systems then that occur as shown in this schematic on the right. If he heats them fast on a wire, you'll see the particles start to heat up and all of a sudden micro explode because I get to a temperature where the nitrocellulose basically starts to decompose and gasify very quickly. And just to show you some characteristics, he's burnt these particles in just a flat flame type burner where he's, say, burning methane, air, diffusion flame, and he injects either nanoaluminum particles or these mesoparticles that have the nanoaluminum particles within them with the nitrocellulose as the interstitial material. And you can just see here, just from the flame heights, the mesoparticles are burning out quicker than just the pure nanoaluminum particles. So the idea is, again, he's exploding the mesoparticles and making sure that they're distributed and they don't have time to sinter. And if you go back to this basically burning time plot on the right versus diameter, this is the characteristic time that he was getting for the nanoaluminum, and his mesoparticles decrease that time by about an order of magnitude for looking at the burning out of the particles. So it's still not down to d to the 1, but it's a significant improvement in terms of just burning the nanoparticles by themselves. And the theory is that he's preventing the sintering of those particles by keeping them separated by the nitrocellulose until it basically gasifies and then distributes the nanoparticles. Here's an example of using self-assembly, of making a fuel oxidizer system. This was based on making a thermite mechanism. And what was using electrostatic forces. So in this particular case, started off with nanoaluminum, nano copper oxide, and the nanoaluminum was coated with TMA, the nano copper oxide was coated with MUA, and the tail ends of the ligands were oppositely functionalized. So one was charged positively and the other was charged negatively. So that when they were added to the same solution, basically the charges were neutralized and basically the charge left to form a salt and the ligands joined together. And so you start off with these 40 nanometer type nanoparticles and you get it to self-assemble into a about a 4-micron particle. So again, a large increase, and basically then the interstitial spaces between the nanoparticles themselves are these ligands. And just to show you, these particles can then be put in a tube, ignited at one end, and they burn very quickly then, going through a very small channel. Another example of sort of a self-assembly process is to take nanorods of copper oxide, coat them with, again, a ligand, then mix them with basically nanoaluminum, and they get the nanoaluminum particles to align themselves on the nanorods. Okay, and if you do that, you can increase, just of this material here, you can increase the reaction rate of the combination of the aluminum and copper oxide in this form versus just mixed physically. Okay, so you can get a large increase in the burning rate. Some other examples of making reactive materials in terms of intermetallics is using basically vapor deposition. And so here are just layers of one material layered with another material. So here a nickel aluminum foil is being made, okay, to form when it's ignited at one end, to form the intermetallic, an aluminum nickel intermetallic. And again, reaction rates are basically controlled then by the length scales of each of these layers. Okay, so you can imagine a reaction wave going this way. Here's the reaction zone interface, and now I've got diffusion to and from that interface that's going to control the reaction rate. Another example of putting intermetallic together, again, an example of aluminum copper oxide and an aluminum nickel oxide using a physical vapor deposition technique. So initially on a silica wafer, copper is deposited, as shown here. The copper is then oxidized to form basically copper oxide nanorods off of the surface, okay, that have diameters of 40 to 80 nanometers. And then a physical vapor deposition of aluminum is used to coat those nanowires, okay? And the same thing has been done with nickel, making nickel oxide and coating the nickel oxide with aluminum, for example, to create an intermetallic reaction. So again, I'm showing you how, in these particular cases, moving away just from the organic material in the metal, but now either a metal or metal oxide to get a thermite reaction and a intermetallic reaction. These could be used, be used as energetic materials in composite materials, or this is also leading to the idea of putting energetics on chips, okay? And using, instead of, say, an electrochemical battery on a chip, can I store the energy in terms of an energetic material like this and basically then ignite it and use that thermal energy to create the energy I need to run a silicon chip or something like that. Sort of a top-down, the approaches I showed you were more bottom-up approaches. People have also looked at top-down approaches, where I start out with large materials to try to make materials that are at the mesoscale with nano features. An example of this is using basically high-energy ball milling, where I might put in, the two materials I want to look at, say aluminum and nickel or aluminum and iron oxide. At the micron size, I basically put them in with steel balls in a mixer, and I basically grind it so that they grind together. And eventually you end up with micron particles with internal nanostructures. Okay, and this has to be a controlled process again, because that, as I mix it, if the balls start heating the substance, I got to make sure I don't have a runaway reaction. So a large range of reactive materials have been produced, and I list a bunch here. You can look through it: boron, titanium, very exothermic intermetallic reaction there. Aluminum copper oxide, different sort of metal oxides have all been looked with aluminum. And you can use a liquid surfactant such as hexane, kerosene, and a type of grinding media are selected to adjust the powder size. So what happens if I put, a liquid hexane in, as I start to grind the material, the hexane actually attaches to the surface and prevents it from growing further and further. So I can actually control the size of the material by having it internally passivate during the bowling process. So this is, again, just showing some design considerations of, if I were to do that bowl milling, and I start creating different types of composite materials. Suppose I did want to add it into an energetic material like a AP composite propellant. And so if I was working with an intermetallic, such as the titanium boron, eventually I want the titanium to go to titanium oxide, and I want the boron to go to boron oxide. But the initial step of going to titanium boron is also very exothermic. And that's going to happen at a lower temperature, potentially, that reaction. So this shows basically the trade-off of the heat of reaction between the components, and then the trade-off with regards to the maximum heat of oxidation. So if I, as an example here, if I take the boron titanium system and I look at its heat of reaction to make the alloy, it's going to come over here to about 4 kilojoules per gram. And then once I react the boron titanium with oxygen, I'll get about 30 kilojoules per gram. And so there's certain combinations that are going to give you a better sort of intermetallic reaction versus oxidation reaction, and vice versa. So there's a lot of, again, design process in the combination of which fuel, which oxidizer I could actually use to have a low temperature reaction, for example, to affect ignition, and then a high temperature reaction to affect the overall energetics of my system. Oh, and I did want to show, if we're talking about heats of reaction, TNT, again, is about 2.7 kilojoules per gram. So note that even the intermetallic reactions here between the metal and metal oxide, or which is the thermite reaction, or the intermetallic between two metals to give the alloy, can be much more than the TNT. Okay, again, another top-down approach using high-energy ball milling. In this particular case, instead of using a metal oxide or a metal combination, the idea of adding a polymer during the high-energy ball milling process. So here, starting off with a fuel-rich aluminum PTFE powder mixture, putting them in a ball mill, and ending up with a mesoscale composite particle of aluminum and the polyfluoride polymer. Looking at the burning rates of adding that to, say, an AP HDPE composite propellant, those particles, you can see if I just add micron aluminum, I get this burning rate here. And with these composite particles of aluminum and a small amount of the polyfluoride polymer, I can increase the burning rate and eventually get to a plateau. The other thing it does is, if I look at the burning process on the right, what you'll see is, much like if I were adding the nanoparticles, or more specifically, those mesoparticles that Mike Zachariah had, what I'm finding is at the surface, here's the burning surface. In the case of just adding the aluminum burns at a far distance off the surface, whereas these composite particles with the polyfluoride polymer mixed at the nanoscale with the aluminum, the particles are burning right on the surface. And what you end up with then, if you look at the final products made, in the case of the aluminum, you get much larger oxide particles And in the case of these composite particles, generally you're going to find smaller oxide particles. Again, the idea that the particles are actually burning at the nanoscale versus at the micron scale. Okay, another idea is making use of graphene as a support. Carbon is also energetic, typically not added by itself in a composite energetic material because the system's already fuel rich, and to get the energy release out, most of it you'd have to go to CO2, which has a high molecular weight. But the idea of actually using it as a support for adding nanomaterial is an example here where if I take the graphene, which is only 1 atom thick, has a very high surface area then, typically 1 micron by 1 micron in the XY dimensions, and I start attaching nanoparticles at the defect sites. Okay, so then the nanoparticles become bonded on the graphene, and as the graphene sheet heats up, and the conductivity of the graphene sheet is very high, but as the particles heat up, they remain pinned at the locations, and again, you prevent the nanoparticles from sintering, and so you preserve the initial surface area. Okay, and there's some examples here where putting different types of catalysts on the surface. So the example on the left is putting a platinum nanoparticle on the surface. The one on the right is putting a polyoxymalate particles on the surface, which are going to be very good for oxidation processes versus pyrolysis processes. And actually, then you could actually layer these carbon sheets into making mesoscale particles with the nanoparticles in between the sheets themselves. Just to give you an example of what's been done there, this goes back somewhat to the use of those iron oxide particles that were passivated, but in this case, this example is being geared towards looking at a hypersonic type vehicle where I want to use the fuel as an endothermic fuel. Okay, so if I have a vehicle that's going very fast, because of the recovery temperature on the surface, the vehicle gets very hot. And so you need to cool the vehicle as well as the engine itself. And so one proposal has been to put structural catalysts on the fuel lines. And then as I pass the hydrocarbon fuel through those fuel lines, the catalyst will start to decompose the hydrocarbon fuel, and an endothermic process, breaking bonds, will occur, which will absorb the heat, which cools the fuselage or the engine. But the problem with that is over time, those structural catalysts start to become coated with carbon deposits. So an alternative to this is to make a consumable catalyst, where you basically add nanoparticles to the fuel itself that are going to act as a catalyst. And so in this particular case, the idea was to take those graphene sheets that had different types of catalyst material on it that would aid in terms of the pyrolysis of the reaction to make it endothermic during the fuel lines. And then when those particles were then injected into the combustor, they could also assist the combustion process to accelerate its low temperature chemistry to make sure it was over within a very short time in the combustor. So here's an example where basically decane was used, in which 50 ppm of this particles were loaded, in which included just the functionalized graphene sheets by themselves, or in which there was a small percentage of platinum put on the functionalized graphene sheets. And if you're just looking at sort of this reactor, which was a reactor had a tube going through a fluidized bed to keep the reactor at a constant temperature, and the composition was measured at the exit of how much conversion of the decane had occurred. And what you find then is adding the platinum FGS had an improvement in terms of conversion and made a significant amount more of hydrogen. And you can see molecular dynamic calculations were also done in which clusters were formed of just the FGS a platinum cluster or the combination of a platinum cluster on an FGS, and the combination actually showed the conversion rate to be the highest for the combination. And when the material got injected into the combustor, a couple other things were noticed. Instead of ignition occurring at one location of the flame and then spreading along the surface, with these nanoparticles added, what you saw was a distributed ignition process where it occurred all throughout basically the spray. And by adding the FGS or the FGS coated with the platinum at different levels, you can see the ignition delay decreased in the combustor, and the percent increase in conversion also decreased with the addition of these nanocatalysts. Okay, so kind of giving you an idea of, taking nanoparticles, passivating them, building them now up to the mesoscale. Now, how do you build them up to the millimeter and larger scale? So very popular now, obviously, is using 3D printing. This is an example of 3D printing propellant with 85% solids loading with a bimodal distribution of AP, and the binder being hydroxyl terminated polybutadiene resin or UV curable polyurethane binder. Compared to cast materials, the printed materials had higher densities and less voids. The mass burning rates between the printed and cast materials were in good agreement. So obviously one of the still problems is, how high can I make these materials and retain their structural form that I wanted. Another example of some work, you can see how you can actually change the porosity. This is just an example of doing it. These are not practical examples. But using a direct right extrusion process, again, AP with ferric acid catalyst. In this case, they've also looked at adding aluminum, HTPB fuel binder with plasticizer and curing agent in the ratio of 78%. Aluminum powder was added in formulations up to 10 weight percent. And freestanding uncured grains were printed up to 100 millimeters in height. As 3D printed densities were 3 to 7% higher than cast grains, and the tensile strength of the printed grain was within 6% of the cast grain. So again, this is a big area in energetic materials, is how 3D printing can start being applied to generate different macroscopic materials. And if you look at burning rates, what you find again is the 3D printed material gives you at least as good or better burning rates. Another example of making bulk materials. I showed you that case where those films were made by vapor deposition of, say, aluminum and nickel, very thin films to make reactive foils. A company was actually made out of that where they would actually use that for soldering electronic components. So you get a very thin film of these very thin layers of metal and another metal, and you'd put it between two components. And what you'd do is you press the two components that you wanted to solder together, and you ignite that foil. And because the reaction wave was so quick, it propagates through, and it would basically solder the two components. Well, you can think of now going to the macro scale of that, and instead of using something like physical vapor deposition, using basically cold spraying techniques. So this is a technique of cold spraying printing of bulk material, which also shows the importance of the microstructure. So how a cold spray system works is essentially, I'm going to inject powder. So I have some sort of a powder feeder here. It injects powder into the throat of a de Laval nozzle, and I have a very high-speed carrier gas that could be heated, and it gathers the particles, and I accelerate them to very high velocities, and then I just use the impact to create the bonding at the surface. And I have basically a system that will go back and forth over it, creating layer after layer, building up the thickness to whatever I want, okay? And then I could actually do machining on it afterwards. So here's a case again where aluminum nickel systems were made. In the first case, nickel and aluminum powders were sprayed separately if you look at a cross-section of what it looks like, you see something like this, where I think the lighter color is the aluminum and the darker color is nickel. If you started off with aluminum particles that had basically a nickel shell around them and sprayed them, you get a cross-section that looked like this. And if you started off with cryomilled aluminum nickel particles, such that the particles themselves already had nanoscale features all throughout them, you got a cross-section like that, okay? And so you can see the mixing has improved in going from left to right as I already changed the microstructure of the original particle. And if you did an experiment where you started to heat up these materials very slowly, and you looked at the ignition temperature, what you find is, I'm showing the three different examples here. So here in the gray, I'm heating up the nickel aluminum particles that were cold sprayed, or that's the green rather, and then the light blue is the nickel clad aluminum, and then the cryomilled nickel aluminum is the dark blue. And you can see that the ignition temperature for the cryomilled is at much lower temperatures. In fact, it's lower than the melting temperatures. Whereas in the case of the nickel aluminum particles that were sprayed separately, you're pretty close to the melting temperature of aluminum before it actually ignites. Okay, so again, that's some examples. Obviously, I'm not going to complete my notes, but I'll give you an idea of what's in these notes, and you can take a look at them later. This set of notes has to do now with the combustion of nanothermites, intermetallics, and porous silicon. And I've already shown you that, or I can show you here. This is the energetics of looking at, say, some intermetallic reactions and some thermite reactions. So if I look at just and compare it to TNT, TNT has a heat of reaction of about 649 calories per gram. If I start looking at different types of thermite combinations, you can see I can greatly exceed the energetics of TNT. And the same thing is true for, I can get close to it with regards to an intermetallic reaction. But if I took the intermetallic reaction, made the alloy, and then let it oxidize, then I'm going to exceed it again like I showed you in that previous slide. Okay, so early on, what people did is they started to take mixtures of these nanoparticles, and what they would do is they would just mix them in hexane and sonicate them to get a good distribution so that they were well mixed, and then they would basically dry off the solvent and create with a well-mixed mixture of nanoaluminum copper oxide. They'd put them in a tube, as I show here. They'd fill this tube up. They'd fill this tube here up with the material, and then they'd ignite it at one end, and they'd look at the rate at which it propagates through the tube. And what you see along the lines of this tube is basically either pressure transducers or diodes that would measure the luminosity of the reaction, so they could actually calculate the propagation rate. And so this gives you an example of the results of that combustion. So on the left-hand side here is basically a plot of the mass weight percent of aluminum. And so what I'm effectively doing is, and this is for a case reacting with moly trioxide, and so I'm essentially varying the equivalence ratio on the horizontal scale, and I'm plotting the propagation velocity. Note that near the stoichiometric condition, the propagation velocity is 1,000 meters per second. Okay, remember that thermite reaction I showed you early on, the first class I was in, basically that at the micron scale, that was maybe propagating a couple centimeters per second. And by going to the nanoscale, I've increased the propagation rate orders of magnitude. And if you change the ratio, you can see the same sort of characteristics of a gas phase flame. As I go lean, eventually I'll get to an extinction limit. As I go rich, I'll also get to an extinction limit. And then the question is, how small a channel can these mixtures of these nanoparticles actually propagate? That's what the plot on the right is showing. So you can see it'll propagate through channels of on the order of 15 micron or less. Again, indicating that very fast reaction. However, if you look at the density, I showed you these powders were just put in that tube and ignited at one end. If you were to pack those powders to a higher density, okay, then what you actually find is the propagation speed decreases for nanopowders, whereas it increases for micron powders that are pressed in a pellet. Okay, and the reason for that is what's controlling the propagation mechanism is different for these nanopowders than for the pressed higher density pellets. And the pressed higher density pellets, basically it's a conduction mechanism, much like your premixed flame in a gaseous system. I conduct heat forward, basically raise the temperature of the material up to some ignition temperature, the reaction rate gets fast, I conduct material forward. In the nanopowders that are not packed to high density, basically I have voids between the spaces of the powders. And so what happens is the reaction rates are very fast locally. And you create a lot of gas locally. Okay, so it creates an overpressure chute, and I use that overpressure chute to create a convective wave upstream. And so instead of conductively heating the particles, I'm convectively heating the particles. So it's a convection wave instead of a conduction wave. And you can get these very high speeds as a consequence of that. That's the same thing that's been seen in granular beds of propellants as well. Okay, and in this plot here, I'm just illustrating that fact. From a high density point, I've got a conductive wave versus a more porous system. I get a very fast heat release locally, and I conduct that wave, or convect that wave very quickly through the material. I'm not sure what happened to my results here. Let me see if I can. Okay, and then you can do, other types of experiments have been done where the pressure of that tube was varied. Okay, and you can see the same thing happens. At low pressures, where the voids do not have high density gas, and so that I can convect very quickly through the voids, the propagation speed's high. If you start increasing the pressure of the interstitial gas, then the propagation speed goes down, right? And you go through an accelerating wave, an oscillatory wave, and then an approach starts looking like a conductive wave. You can look at different types of combinations of oxidizers, and obviously certain oxidizers have higher propagation rates. Here, aluminum with copper oxide, 1 kilometer per second, with moly trioxide, 1 kilometer per second, but with iron oxide only 0.1 meters per second. Okay, so, and one of the questions that comes about is, what's more important in terms of size distribution? Is it the size of the copper oxide, or is it the size of the aluminum particles that's driving the system? What's the rate limiting step in making these reactions go fast from a chemistry point of view? So what you typically will find, if you look at these different systems, it's the oxide that basically releases oxygen at a low temperature. And that oxygen is then transported to the aluminum through some sort of diffusive or convective mechanism that then does the oxidation process. So what becomes very important then is to have a lot of surface area, small dimensions of the oxide particle. And this is just showing some equilibrium calculations. At what temperature does these oxides decompose then? And here's some results of burning rates then, and looking at a combination of micron aluminum with micron copper oxide, nanometer aluminum with micron copper oxide, micron aluminum with nanometer copper oxide, in nanometer. But if I compare this system versus this system here, you can see it's the nanometer copper oxide that's more important than the nanometer aluminum, okay? And that's because it's really the release in these systems of getting the oxide available to react with the metal. Okay, the one last system I'll talk about here that people have looked at, and this goes back to putting energetics on chips, is to use silicon as a fuel itself. So in silicon, I can etch it, chemically etch it, and make nanopores in it. And what people have done is they've filled those nanopores with different types of oxidizers, for example, perchlorates and things like that. And so you can imagine then I could actually put on a chip in a local region. I could create nanopores, I could fill it with an oxidizer, and I could store energy there until I needed it. I'm not going to go through all the details because I don't have time. I did want to show you some examples of propagation. So you can see here what people have done is they've taken a silicon wafer, they've masked off a certain region, and in that strip in the center here, they've etched it to create nanopores, and they filled it with different types of oxides, and then they ignite it at one end, say with a copper deposited copper film here. They heat this, it ignites, and it propagates down. And again, you can see then the wave propagating down that film. And you can get, again, because of this length scale of the pores, you can again get propagation speeds of 1,000 meters per second or so. And those, when you calculate those speeds, particularly in a two-phase mixture, you're getting close to detonation speeds for that two-phase flow mixture. This plot here shows the size of the pore is important to get to high speeds. So again, it's a length scale problem where how far do I need to diffuse reactants? One thing I did, this calculation here shows, if I break the pores up into a matrix like this, where there's a pore here, pore here, pore here, and I filled this with oxidizer. If you do some simple calculations, what you show is you only need to consume maybe one layer of atoms in each of these cells to raise the temperature high enough to propagate that flame at very fast speeds. Okay, because again, there's little mass here in terms of what's being heated up, and the exothermicity reaction is very high. Here's an idea of combining a deep reactive ion etching with electrochemical etching. And so what was done here was a silicon wafer was taken, a mask was put on it, and then what was created was pillars through a deep reactive ion etch, and these pillars were of the micron size, okay? And then after the pillars were made, an electrochemical etch was done. So each of the pillars now had nanopores, and in between the pillars were nanopores. And those nanopores then were filled with an oxidizer. And the effect is, what was the importance of having a multi-scale system? Okay, did having a microscale feature with the nanopores affect the burning rate? And I'm not going to be able to show it here, I don't think. Let me pop back real quickly to the others, see if it works. So here you can see the pillars on the top. They were nanopored. That's what the nanopores look like on the pillars. If you look from the top down, you get this organized matrix structure. And if you actually now look on top here, this is what the structure looked like. If I look at a side view of this burning upwards, this is what happens. So in the beginning, it's already burning at about 2.5 meters per second, which is fast, through just the nanopores. The nanopores here are about 10 micron in diameter, so they weren't the optimal for the highest speeds. And so it's propagating upward. And when it reaches you get an acceleration. So in this region down here, because the pores were large, you had a conductive mechanism. When I got up to the pillars around it, the reaction around the pores were very fast. It created a convective wave through the pores that preheated the pillars upstream. Okay, I'm supposed to end now, I guess, right? What time's the class go to? I got 10 minutes? Okay. Okay, the other feature of these is what happens above the surface when that wave was going so fast. And if you look at this very close, this is one of the high-speed waves moving forward. And you can see it actually creates, because the gas is coming off the surface of the wafer, it creates a shock that now is moving ahead of the reaction front end of gas above the surface. And what's kind of interesting then is suppose I make a system where now I have the poured silicon and the oxidizer mixed here, and I remove the oxidizer from this region here, and then I add it back here. So the question is, if I start this fast wave up here that creates a shock, there's no oxidizer here, so there should be no reaction. Can I recouple this shock wave with the reactive wave to accelerate it again? And you can see that's exactly what's happening here on the right. This wave is going very fast. It approaches. You can see the shock and the reaction are very closely coupled. When it hits this region here, there's no oxidizer, so you see the separation of the shock wave in the chemical reaction. And as I get through here, once it reignites, the chemical reaction recatches to the shock wave, which is very hard to do. Okay, so one of the questions that still remains in these sort of experiments is, what is the origin of the high-speed reactive waves? You can a conduction process, this is without the pillars. So if I have basically a strip here, and it has the nanopores that are 2 nanometers in diameter, and I fill it with an oxidizer. This speed, if it goes up to, say, 2,000 meters per second, what's the mechanism? Can conduction be that fast? So that was a good comment. Somebody said radiation. That potentially, if I have that flame off the surface, I could be radiating upstream. If you look at also the way that nanopores are formed, I didn't show you. If I look at the surface, if a pore comes down, you can have legs between the pores like this that might interconnect below the surface. And so the question there is, are these pore diameters large enough to have any sort of convection wave go through them? And it's highly likely not, because they're probably not much bigger than maybe a few atom diameters, and so you're not going to be able to get a very high speed. So that question still remains: is what's creating the high speeds without that multidimensional characteristic to it with the pillars? And radiation could be a good reason. You could also potentially be cracking the silicon wafer because of the heat stressing, and that crack could form basically an interconnect downstream in which you could now have a convective wave. But anyway, there's a lot of uncertainty and interest in. People have been using, the last things I showed you, the people have been adding those materials to micron systems. And without I'll stop within 2 slides here. But here are energetics, again, of looking at energetic materials versus other ways of storing energy. So if I look at piezoelectrics, the energy density is like 10 to the 5th joules per meter cubed. Look at electrostatics, electromagnetics, shape memory alloys, energetic combustion, nanoporous silicon. You can see the energetic materials store an enormous amount of energy compared to those other mechanisms. And so now the question is, how can I start using that material at a small scale? Okay, because what's an energetic material do? It creates heat. How can I use the heat? Can I basically, use it in a thermopile to create basically an electrical signal? It can create gas. Can I use that gas to propel in some way? And it can create different types of gas, specific type of molecular structures. How could that be used? And people are looking at all those different types of systems. I mean, one example that people have looked at is making a little hopping sensor. And again, this has potentially, I guess, putting a sensor out in a field. And it might sit out there for a long period of time, so that if I had an electrochemical battery, it would dissipate. But if I store it in an energetic material, and if I tune it to a flash of light or something that happens, I could fire off the energetic material. That could create gas, and then if this thing is sitting down in grass or something like that, it could hop up and get out of the grass and then activate a sensor. So that people are looking at using it for igniter systems, a number of different functions on a chip, opening in a valve, for example. I fire a valve and it basically opens up a valve system. And all those, I give examples in here. I don't have time to go over them. But I think if you're interested, there's references there. You can read through it. I put a number of references in that last file. They're basically overall sort of books. I think if you go through that, you'll find a lot of interesting information as well. So, sorry I didn't get through it all, but I think I covered enough that if you had no experience in this area, you can see that there's a lot of applications. It's just not using it for military purposes. There's a lot of interest in space now. Space being really the next frontier in many ways, and how it can be used. And so this work can apply in many different ways to that. Okay, so with that, I guess let's all go get lunch. Thank you.